Hello everyone, in this video we are going to be looking at the differentiation from first principle. Now differentiation is all about the rate of change of a particular function. Now if you have seen a graph that looks like this and you're asked to differentiate the function of this particular graph, what they ask you to simply do is to find the slope of that graph. And from basic algebra, we know that the slope of a particular graph is gotten by taking 2 points on the graph. And this is called the slope of a secant line, which we know as the change in y divided by the change in x, and it is equal to y2 minus y1 divided by x2 minus x1. Now, this is what we know from basic algebra. But what about if you're asked to take the slope of the tangent line? Now, the tangent line, unlike the slope of the secant line, is just a single point, and it is given as the derivative of that particular function that was used to sketch out the graph. Now, we are going to first derive a formula that explains the slope of the tangent line using what we know from the slope of the secant line. Now, from basic algebra, we know that y is always a function of x because the y-axis changes as the x changes, and that is why we have the change in y divided by the change in x. So since y is a function of x, I simply say y is equal to f of x. And from that, I can say that my y1 is equal to my x1, while my y2 is equal to my x2. So from this, also, I can rewrite my change in x, which I know is x2 minus x1. I can rewrite it by making the x2 subject of formula, and x2 will be equal to x1 plus the change in x. Now, this is what we got from this simple, you know, display of expressions that we have done here, because we know that from the secant slope here, that change in y is equal to change divide by change in x is equal to this particular expression. Now, for my y2, recall I have replaced it with f of x2, which is what I have done here, and my y1 I replace with my f of x1. So you can see that I am not changing anything here. So the equation still remains the same. So all divided by my x2 minus x1, which is simply the change in x, and that is what I have written here. Now, for my x2 here, we can see that I made x2 to be equal to x1 plus change in x. And because of that, I replace it here, which leads me to the second or a more simplified form of this particular expression here on the right hand side. So we have f of x1 plus change in x minus f of x1 all divided by change in x. Now this is what we got if we interchange quantities of y to f of x. But if we look at the graph which I have drawn here, though I have given us another sketch of graph here to make it more easy to understand. Now, if I move this my y value here, because I said y is a function of x, if I move this my y value here, recall that this is my change in y and this is my change in x. So if I move this my y value here and bring it down to approach the P point here, we can see that as I bring this point down, that the change in x becomes smaller and smaller until it tends to zero. And that is what we call a limit. The limit of the function change in x tends to zero when I move this point down. So because of that, for the sake of accuracy of our value, we set the limit of this particular equation here as change in x tends to 0. So we say limit as change in x approaches 0 of dy dx, or rather change in y over change in x is equal to this same function here, which I have given us. And this is what we call the differentiation from the first principle. Now this formula here can be used to differentiate any function of y with respect to x. And we can see from this example here, we are given y equal to x2. And remember I said y is a function of x, so f of x is also equal to x squared. And now from this formula which we have derived here, I can say my change in y over my change in x is simply equal to this particular expression. Now we can see that this expression does not change. But what affects this expression is the square here, which I have put here, and my f of x is here, is also x squared. So whatever I am given here, be it square root or cube root, it's what I am going to replace here. So if I'm giving a square root here, I just put a square root here. But in this case, I am giving a square. So I put my x plus change in x, then the square, minus my f of x, which I know is x squared, all divided by my change in x. Now, if I simplify, or rather expand this expression from my knowledge of algebra, I will discover that I have x squared plus 2x change in x plus x change in x squared minus this particular quantity x squared, all divided by change in x. Now we can see this is simply algebra here. When you expand and you open the brackets, you get this function here. Now we can see that we have a positive x squared and a negative x squared, which cancels out. So once these two cancels out, it leaves me with this in my numerator, 2x change in x plus change in x squared divided by change in x. Now we can see here that if I factor out change in x, because change in x is here and it's also here. So if I factor out change in x, which I have done here, I will get this particular function here. So once I have factored out this change in x, I simply cancel this change in x. So leaving me with this 2x plus change in x. And this, I set my limit of this particular function as change in x approaches 0 of dy dx, or rather change in x divided by change in y divided by change in x equal to 2x plus 0, since I have set the limit here to approach 0. So this becomes 0 here, and leaving me with my answer 2x. So I say therefore my dy dx is equal to 2x. Now we quickly look at a different example